This is one of a series of revision vignettes intended for my design classes I teach at North Carolina State University. This particular revision vignette is about high-level decision making about how to implement a particular function. When do you choose hardware over software? And if you're choosing hardware, how do you choose amongst an ASIC implementation, a gate array, or an FPGA? This slide discusses the trade-offs of hardware versus software. The top few lines are the pros of each, the bottom few lines are the cons. Obviously with software, you will have the lowest engineering cost, the lowest upfront cost for implementation. Thus, in general, you'll choose software over hardware if software is suitable. In addition, you have retained significant advantages of flexibility and the fact that bugs can be fixed later in the field by shipping patches to your customer. On the other hand, software does not always meet the performance, power, or production cost target of a particular application. What I mean by cost target here is the cost of the hardware on which the software has to run. If you need a large multi-core computer or an array of multi-core computers to meet a particular performance target for a particular software implementation, then you may choose a more direct implementation of those functions in hardware. Thus, hardware is used primarily when it's the only way to meet a performance, power, or a cost target. And quite often this distinction is very clear. If the software can meet it marginally, you'll often tend towards the software solution. Thus, you tend to use hardware when you need it to meet a specific target, and the reason why you choose it carefully is that it has a much higher engineering cost per function than implementing a function in software. And we particularly refer here to the upfront engineering cost, the cost that is incurred before you ship any product to a customer. This is referred to often as the NRE cost, or the non-recurring engineering cost, that is, the one-time cost for implementing the function upfront. I do point out at the bottom here that most systems really use a combination of hardware and software. You often have embedded CPU or CPUs running even in a digital chip that's intended mainly for one application, and this is performing a large variety of functions better suited for software. And you'll build hardware accelerators for those functions where you cannot meet the performance, power, or cost any other way. So here's an example. Let's say we're building a camera recorder chip for use in a high-definition video cam. There's a step in camera recording, or more precisely video compression, called motion estimation. On full rate, full screen video, motion estimation by itself requires 9 billion operations per second, or 9 GOPS, or 9 giga operations per second. This would be very difficult to achieve even in a 4-core, 4 gigahertz CPU. Because remember, no CPU can run, it's difficult for a CPU to run much more than 1 to 2 operations per cycle. And even that can be difficult. And this is only one function to produce a video in a compressed format. And it has to be done in real time. Thus, this type of function would be implemented in hardware. Other examples include mobile application processor. Will actually be a mix of hardware and software. 3D video encoder is an extension of what's discussed above. High-resolution graphics engine. This is a good example. Your demand for performance in graphics is essentially insatiable given today's technology. And your power requirements are very steep. In a desktop solution, it has to be coolable by a fan. In a mobile solution, it has to be coolable within the confines of a mobile phone and not deplete the battery too rapidly. all this combination of things that graphics engines are much better implemented in hardware than in software. Self-driving automobile processor would have to do a lot of video computations in order to properly understand the scenery around it. Smart grid power conditioner controller has actually to work at a fairly high data rate. A network security engine could only be implemented in hardware to meet performance requirements for a high-end security engine. I'm talking about one here that actually tracks the packets going through the network. That'll be the level of performance needed will be only implementable in hardware. Now let's turn to the different types of hardware. In order to understand this, we briefly have to review how chips are made. The design is reduced to a layout that is a representation of the masks that are eventually used to print features on the chip using steps called photolithography. An example in the layout is shown on the right. The blue, this is an inverter with an NFET and a PFET. The blue are built in the metal mask. There's a polysilicon mask, that's a conductive form of silicon, that is used to connect the gate inputs. And that is its own mask. And there's various implants for the N and P materials required to define the transistors. And each of these will have their own masks. And the mask is shown in the center here. It is a transparent structure through which you shine light to produce an image on the chip that is then used to define where the metal has been put down, where the boron is put down, where the phosphorus is put down, and so on. And these masks are produced from the layout. A modern chip might have 20 or more masks involved in its manufacture. Then these chips are made serially in a factory to produce a silicon wafer, processed silicon wafer, as shown on the bottom right. Now, why do I go through this? Because it relates very strongly to three main hardware styles and how much processing they have to go through in the factory to get your part back. In a standard cell ASIC, every transistor, every piece of metal, every piece of polysilicon is fully defined from scratch using a set of standard cells. On the right I show a D flip-flop and a gate. So because the entire chip mask set is defined from scratch, you have to produce an entire set of masks, and it takes some time to run the process through the factory to produce the first batch of chips from these masks. And just these steps themselves of sending a design to a factory and getting the first chips back can cost millions of dollars, or possibly hundreds of thousands if it's a lot that's shared with other projects. And the tasks of designing the parts up front can be very expensive, $20, $30, $40 million. And the reason for this is partly because these will be large complex chips, because that's the only time this is justified. Secondly, it's very hard to fix the problem if it comes back from the factory bad, so you spend a lot of time verifying the chip before it goes to the factory. The next alternative is a gate array. In a gate array, a set of gates or transistor logic functions, as described in the right there, are predefined and pre-placed in the silicon, and a set of wafers are actually made with these functions sitting on them. Arrayed, these gates are arrayed across the wafers. And these wafers are kept in the factory until a customer comes in and says, this is how I want these functions connected up to meet a particular function. Thus, the number of masks involved is only a handful, 4, 6 or so, and the turnaround time to get the first parts from the factory is much faster. The third alternative is a field-programmable gate array. These are pre-made chips that are shipped to you, and you have chips sitting on your shelf. They're programmable logic chips. You can program a very wide variety of logic functions into these chips. Obviously, when you build a logic part in an FPGA, you don't have to send any masks to the factory at all. So that there's no complex mask steps involved, and no time delay in getting the first parts back from the factory. This table summarizes the positives and negatives for each of these three hardware implementation types. Starting with a standard cell ASIC, what are the positives? Well, the biggest, most important positive is you get the highest level of performance. You can have a billion transistors or billions of transistors operating at gigahertz or multi-gigahertz rates to do things such as high-end network processing, for switching, for example, or graphics. You can achieve the lowest power per operation. And often this is the only way to meet a specific specification. For example, in the high-def video camera application we describe it. It also gives you the lowest volume, lowest cost per die or per chip, but only at high volume. It costs $50 million to get the first chips back. But after that, your processing cost per wafer is only a couple of $1,000s per wafer, $1,000 to $2,000, depending on the masks, on the steps involved. And you might have 1,000 plus chips per wafer. So the cost of making them is only a few dollars per chip. The negatives for a standard cell ASIC are that you've got a very high design, CAD and wafer costs before you get a single part back from the factory, and from a cash flow perspective, before you can sell a single part to a customer. There's also a long time to market. These will take 12 to 18 months to design, and you'll have 1 to 3 months in the factory before you get the first part back. So in general, standard cell ASICs must be addressing large, relatively stable markets, and in these markets, this must be the only way to meet the performance requirement. In contrast, going to the right-hand side, in FPGA, the positives and negatives are almost inverted. You have very low design costs, possibly just tens of thousands of dollars. Simple tools, cheap tools, they actually give them away, in the whole. And you can design something relatively quickly. Right? If you got the design done, you can make your first part the same day and test it and debug it in the actual hardware, rather than doing a lot of simulation like you would in a standard cell ASIC. The negatives of the FPGA is it's much lower performance than an ASIC. You're only talking about the equivalent of millions of implemented logic gates, not up to a billion of gates. And you're only talking about speeds of, say, 100 to 100 megahertz. In addition, you have a high per unit cost that does not go down with volume, at least significantly. And it can be thousands of dollars for the larger, more complex FPGAs per unit. So in general, FPGAs are very useful when you have a market that is small, low volumes, and you can meet the functions in an FPGA or a set of FPGAs. Or you have a market that's changing fast, and thus you need a short design cycle, an implementation cycle. Gate array is in the middle here because it's kind of in the middle. Costs less to make than a standard cell ASIC. You get it back faster. Not quite as cheap as a standard cell ASIC in volume, but in mid volumes it can be cheaper. The performance is more than an FPGA, but not necessarily a lot more because it's still predefined functions. One application of gate arrays, by the way, is an FPGA shrink, if the market volumes benefit from that. Here's a slide from a vendor, Express Array, saying that the average asking price, or the cost per part as a function of volume for an FPGA, a gate array, in particular the Express gate array, and a standard cell component. And one thing to remember is that you have to recover your upfront engineering costs in your selling price. And these upfront engineering costs, or non-recurring engineering costs, or NRE, are much higher for standard cells than FPGA. And even the gate array has a higher NRE than an FPGA. So you can see here the FPGA line, for example, is cheaper at modest volumes, a few thousand. But because the cost per part doesn't scale with volume, it's much more expensive when you go to high volumes. In contrast, the standard cell design is the cheapest per part at high volumes. And remember, furthermore, it might be the only way to meet a specific performance or power requirement. And in between is the gate array. The gate array is significantly cheaper per part than the standard cell design in volumes up to a few tens of thousands, and is cheaper than the FPGA in modest volumes of even a few thousand. So this shows that the trade-offs in cost per chip, or selling cost price per chip, as illustrated in this specific example. Be careful, of course. Any specific example might be quite different from this one. This is a relatively modest FPGA, for example. It's not one of the high-end FPGAs. And this is assuming that you can actually implement the required functionality in all three design styles. So your particular graphs could vary quite differently from this. So let's finish this off by looking at some examples. A video encoder for a handheld camera. Would you implement that in hardware, software, FPGA, standard cell design, or a gate array? Well, we've actually already discussed this, and a standard cell design, often referred to as an ASIC, application-specific integrated circuit, would be the most appropriate implementation. Next, a logic chip for a low production run jet fighter. By definition, all jet fighters are low production runs, a few hundred, few thousand units. This is specifically referring to hardware, so we're talking about an ASIC using standard cells, a gate array, or FPGAs. Well, at a few hundred units, you're going to try to use FPGAs as much as you can, and this is, in fact, what actually happens. In a lot of military equipment, FPGAs are very dominant. Alternatively, a graphics processor for desktop or mobile. Which style would you tend to use? This would be an ASIC, standard cell style, because you need the absolute in performance and power per performance. Next, a high-level processor for a networking switch. These have to be able to manage a reasonable number of packets, but are dealing with more application level issues rather than just shifting packets around for routing or other very well defined examples like that. And this might be a market where you actually have to adapt your equipment quite rapidly to changes in customer requirements. So which implementation style would you use? Well, performance demands hardware, but the flexibility and rapid market change means you have to use an FPGA. Next, an audio processor for speech recognition. Which style would you use? Speech can be captured at sampling rates of 8 or 16 kilobits per second, or kilosamples per second. Is that going to be performance taxing on even a small processor? No. Thus, you'd implement in software. Finally, a medical processor of 100,000 unit volume. You might care about power here, it might be portable. The volumes are modest, but not small. What might be a good implementation style here? A gate array often suits these mid-volume applications. Well, that's the end of this revision vignette. I hope it was useful to you. and others will be appearing here in the future. Thank you.